Hello there, Mr. Sutton here, bringing you the AB Calculus 411 Extra Practice Number 4 solutions on L'Hopital's rule. For this free response problem, the depth of a river at a certain point is modeled by the function W, this piecewise function up here, and W is measured in feet, time is measured in hours. First task, we want to find W prime of 8 and then explain what that means. Alright, well, if I want to find the derivative of 8, since this is a piecewise function, I have to look in the rule where 8 falls in terms of the domain here. That's going to be the second rule, so I need to take the derivative of this second rule here. That's going to be, so for 6 to 10, the derivative, W prime in general, is going to be negative 2/5 times t minus 6. And I'd have to multiply by the derivative of t minus 6, but that's just 1, so I'm not going to bother. So there's W prime between 6 and 10. Now W prime of 8 is going to be basically this, with 8 plugged in for t. And you could leave it like this, or you could simplify this to negative 4/5. Now in terms of units, this is the rate at which the depth of the river is changing. So that's going to be feet per hour, so negative 4/5 feet per hour. And just to explain the meaning of this, we have to include the time as well. So we can say at 8 hours, the depth of the river is changing at a rate of negative 4/5 feet per hour. For this problem, we're told that the graph of W is concave down on the interval from 3 to 3.5. They want us to use the line tangent to the graph of W at time 3 to show W of 3.5 is less than or equal to 9. So they're pretty much telling you how to prove this statement right here. We want to use a tangent line at time 3. So how about we go ahead and get a tangent line from time 3 and then just see what happens if I plug 3.5 into it, and we'll go from there. So to get that tangent line, I need to know W of 3. In general, I'm going to have W of 3 plus W prime of 3 times t minus 3. So W of 3, I'm just going to plug 3 into the W function using this first rule. That's 17 minus 3 over 2 cosine of 3 pi over 6. Well, this is really cosine of pi over 2, which we know to be 0. So this is really just 17 over 2 when all is said and done. And now I also need W prime of 3. Well, for the interval from 0 to 6, W prime of t in general is going to be, let's see here, this 17 over 2 is gone because it's a constant. We've got, using the chain rule here, this is going to be positive 3 over 2 sine of pi t over 6 times the tail of pi over 6. So that ends up being 3 pi over 12, which is pi over 4. So we end up with pi over 4 sine of pi t over 6. And then if we plug 3 into this function, well, sine of, this is essentially sine of pi over 2, that's going to be 1. 1 times pi over 4 gives us a derivative of pi over 4. So now what is the tangent line approximated value of 3.5? That's going to be approximately W of 3, so 17 over 2, plus W prime of 3, pi over 4 in other words, times t minus 3, so in this case 3.5 minus 3. And that's going to come out to, let's see, this is essentially pi over 4 times 1/2, 0.5. This is 17 over 2 plus pi over 8. And at this point, you know, where do we go with this tangent line approximation? So this is where we have to kind of see where we're going in order to know what the next step is, because it's kind of tricky at this point. So our ultimate goal, we want to show that the true value of W of 3.5 is less than or equal to 9. Now the way we're going to do this, since this function is concave down, and we'll spell all this out in a minute, but since this function is concave down between the launching off value for your tangent line and the number you're plugging in, that means that any tangent line approximation at 3.5, since we're concave down, the tangent line is going to overshoot the true value of 3.5. So if you want to show that 3.5 is less than a certain number, you need to show that your tangent line approximation equals that number, or something less than that number itself. If we can show that 3.5, W of 3.5 If we can show that the tangent line approximation is 9 or something less than 9, since the tangent line over-approximates this value, that will also prove that W of 3.5 is less than or equal to 9. So that brings us back here. Is this equal to 9? Not exactly. If you had 17 halves plus 1 half, that would equal 9. But here's the good news. Pi is about 3.14 and some change. Pi over 8 is less than 1 over 2. It's less than 4 over 8, and hence less than 1 over 2. So we can say that this tangent line approximation is less than 17 over 2 plus 1 half is less than essentially 9. Now here's where we get to the proof part of it. W is concave down on 3 to 3.5. This proves that the tangent line over-approximates the true value of W of 3.5. And since 9 is over our over-approximation, this proves that W of 3.5 must be less than or equal to 9. For this last part of the problem, the final boss battle of this free response, they want us to find the limit as t approaches 2 of all this craziness. Well, we can see very quickly that when you plug in 2 for t, you're going to get 0 in the denominator. I've got a sneaking suspicion that's going to happen in the numerator as well, so I'm probably going to have to use L'Hopital's rule to evaluate what's most likely going to be an indeterminate form. Since I'm anticipating this, let me just go ahead and take the limit independently of the numerator and denominator at t2. So limit as t approaches 2 of my numerator, that's going to be, let's see here, 17 over 2 minus 3 halves times cosine of 2 pi over 6 minus 8, that's going to be 2 cubed, plus that 1/4. Now, does this actually all come out to 0? Well, let's start with this cosine function here. So this is cosine of pi over 3, or cosine of 60. I know that to be 1/2. So we're really doing 17 over 2 minus 3 over 4 minus 8 plus 1/4. Negative 3/4 and positive 1/4. That's going to be negative 2/4, or negative 1/2. 17 halves minus 1/2 is 16 halves, which is 8. And then if I subtract 8, all of that does indeed come out to 0. So just make sure you verify that that's actually 0. Now the other one's a little bit easier. Limit as t approaches 2 of t minus 2. That's just going to come out to 0, 2 minus 2. Therefore, because the numerator and the denominator both have limits of 0, we can use L'Hopital's rule to evaluate this limit. So we're going to have the limit as t approaches 2, and now we're actually going to have to take some derivatives here. In the numerator, I'm going to have w prime minus 3t squared, and in the denominator, derivative of t minus 2 is just 1. So recall from part B that w prime, at least between 0 and 6, equals this. And that's all we care about because time 2 is on the interval from 0 to 6. So that means that I can write this as pi over 4 times sine of 2 pi over 6 minus 3 times 2 squared, just plugging 2 into all of that stuff. And this is actually all constants at this point. So you could call it a day and just stop the problem and be done and collect your winnings. If you wanted to simplify this, you can go a little bit further. This is really sine of pi over 3, or 60 degrees, which is going to be radical 3 over 2. So this is going to be pi radical 3 over 8. This over here is going to be minus 12. So you could go a little bit further, but this is as good as it gets. For this free response problem, we're given the function f of x equals e to the x times cosine of x, and our first task is to find the average rate of change for this function on the interval from 0 to pi. So in general, that's going to be f of pi minus f of 0 over pi minus 0. And to get credit, we just have to plug pi and 0 into the function. So we're going to have e to the pi times cosine of pi minus e to the 0 times cosine of 0 all over pi minus 0. And if you wanted, these are all constants, so you could stop right here and just call it a day. But if we want to simplify, cosine of pi is -1, so this is negative e to the pi. This is going to be over here, cosine of 0 is +1, so this is going to be -1 when all is said and done. This is pi down here. So we have negative e to the pi -1 all over pi, and that's about as good as it's going to get. On this problem, I want the slope of the tangent line for the graph of f at 3 pi over 2. So for that, I just need to take the derivative of f prime, and plug 3 pi over 2 into it. That's going to require the product rule, u prime v plus uv prime. Let me set up my box and ribbon to help me with this. So I've got u and v, e to the x, and cosine of x. And I've got u prime and v prime down here. That's going to be e to the x, the derivative of e to the x. And then derivative of cosine is going to be negative sine of x. Multiplying it out with the ribbon, this is going to be e to the x cosine of x minus e to the x sine of x. And at this point, I just have to plug in 3 pi over 2. So this is going to be e to the 3 pi over 2 cosine of 3 pi over 2 minus e to the 3 pi over 2 sine of 3 pi over 2. At this point, you've got all constants. So you could stop here and be done with this problem. But if you wanted to keep going, cosine of 3 pi over 2 is 0, which is going to zero out this whole first term. Over here, this is sine of 3 pi over 2, that's -1. So we have e to the negative 3 pi over 2 times -1. And all of that is just going to come out to positive e to the 3 pi over 2. For this part of the problem, we're trying to find the absolute minimum value of f on the interval from 0 to 2 pi. So for this, we're going to be using the candidates test. We're going to have to test out 0 and 2 pi, the endpoints in the original function, and we're also going to have to test out any critical values. Let's begin this process by finding critical values. So for that, we're going to use f prime, and we actually figured out what f prime looked like in part B. It was, again, e to the x times cosine of x minus e to the x times sine of x. So we're just going to set this equal to 0 now and solve for critical values. So we can start by factoring an e to the x out of all this, leaving me with cosine of x minus sine of x inside. We know e to the x cannot equal 0, but cosine of x minus sine of x can. To solve for x in this situation, a little bit tricky, but if you've done this before, you kind of know the routine here. We have to add sine of x to the other side, and then we divide by cosine of x. Now, the reason I'm allowed to divide by something with a variable here is because since sine of x, that's the y value on the unit circle, and cosine is the x value, since these are on the unit circle, these can't both be 0 at the same time, or you would no longer be on the unit circle. And since they equal each other, if they can't both be 0 at the same time, that means neither one of them can be 0. So we're guaranteed we're not dividing by 0 when we divide by cosine of x. So that would leave us with tangent of x equals 1. And then if I take inverse tan between 0 and 2 pi, that's going to give me pi over 4, and also the third quadrant version of this, where tan is positive, 5 pi over 4. So pi over 4, 5 pi over 4, basically 45 degrees and 225 degrees. So that gives us 2 more critical values on the interval from 0 to 2 pi. All right, time to test all of these out. So if I test out 0, my first endpoint, e to the 0 times cosine of 0, that's just going to come out to 1. Next, testing out pi over 4, plugging that into the original function here. That's e to the pi over 4 times cosine of pi over 4. And we are going to have to simplify this stuff enough that we can compare it to other things. So I know cosine of pi over 4 is root 2 over 2. So this would be radical 2 over 2 e to the pi over 4. That is going to be difficult to compare to other things, but we're just going to have to go with it. Now let's do f of 5 pi over 4. That's e to the 5 pi over 4 times cosine of 5 pi over 4. And this is kind of similar to this other answer, except that now we have e to the 5 pi over 4, and the cosine of this stuff This ends up being the negative version of what we had when we did cosine of pi over 4. This is basically quadrant 3 version of 45 degrees, and cosine is negative over there. So this then ends up being negative root 2 over 2 times e to the 5 pi over 4. And then finally, we have to do f of 2 pi. So e to the 2 pi cosine of 2 pi. And cosine of 2 pi is the same as cosine of 0, which is 1. So this all just comes out to e to the 2 pi. Now we have to compare these, and we were looking for the, let's read this again, the absolute min. So let's pick the lowest one. So it's kind of hard to compare all this stuff with e's and radicals, but we notice that out of all these four possibilities, these four candidates, only one of them is negative. This one right here. So I don't know what these all come out to in terms of decimals and numerically, but I do know that a negative number is always going to be less than a positive number. So this negative one has to be our absolute min. For the last part of this problem, all of a sudden we're given a new function, g, which we're told is differentiable and has a function value of 0 at pi over 2. We're also given the graph of g prime. Cool. We want to find the limit as x approaches pi over 2 of f of x, which we already knew a little bit about, over g of x. So just thinking what happens mentally about when we plug in pi over 2 to both of these, right away we can see that when we do g of pi over 2, just plugging it in, that's going to come out to 0, which is no good. So this is probably going to be one of those indeterminate forms that I'm going to have to use L'Hopital's on. So I'm going to go ahead and just take the limits of the numerator and denominator separately and just start my whole L'Hopital's process for this. So the limit as x approaches pi over 2 of f of x, basically plugging pi over 2 into the f of x function up here. Cosine of pi over 2 is 0, so that's going to zero out all of this and give us 0 for that limit. Now, how about the limit as x approaches pi over 2 for g of x? I can't just say that it's 0 based off of what they've told me so far, because we don't know what g of x actually does algebraically. We only know this one function value. We do know a little bit about g prime, but that doesn't necessarily tell us everything we want to know about the g function. So the key on this one is that g is differentiable. Because g is differentiable, that implies that it is also continuous. And because g is continuous, continuous means function values and limit values are the same thing. So that means that the limit as x approaches pi over 2 of g of x and g of pi over 2 have the same value, which we know is going to be 0. So now that we've proven that the limits of the numerator and the denominator are both 0, we can use L'Hopital's rule to evaluate this overall limit, which means basically we're going to take the limit as x approaches pi over 2 of f prime of x over g prime of x, just taking those derivatives independently of each other. Okay, well, if I plug pi over 2 into f prime, from part B, here's what f prime looked like. That was e to the x cosine of x minus e to the x sine of x. So we're just going to plug pi over 2 into all of that stuff. And we can do this because we've already defined f prime back in part B. So there we go for the numerator. We'll clean up that mess in a moment. Now for the denominator, we have g prime limit as x approaches pi over 2. Am I allowed to just write g prime of pi over 2? It turns out I am, because I have a graph of g prime where I can clearly see that we are continuous at pi over 2. So I'm allowed to just say the limit and the function value are the same thing based on what I observe in that graph. All right, let's go ahead and simplify this a little bit. So cosine of pi over 2 is going to be 0. That zeroes out this whole first term. And then over here, sine of pi over 2 is 1. So my numerator then is just going to be this negative e to the pi over 2. In the denominator, g prime of pi over 2, we can look that up directly in the graph, and that's right here. That's a value of 2. So there's our final simplified answer.